Okay, what I want to do in this final review is just go over about 2025 problems to kind of tie any loose ends. So as you can see, the first question is you have an acyl chloride that's reacting with some kind of a Lewis acid, and it's giving you two species. It doesn't matter what these species are, the questions are pertinent to what you have learned in Organic 1. The question is, in the above reaction, choose the correct statement about the ion 3. So this species is what they're looking at. Notice that if you have to write down the Lewis structure, because everything about the choices are essentially pertinent to hybridization. So this is the Lewis structure that you could draw, or you can say that essentially the electrons can be pulled, and in that case, the positive charge would be on carbon. And so if you think about the kind of geometry and the kind of hybridization, you can perhaps just count your steric number. You have an electron group over here and another electron group over here. That means your steric number is only 2. And if it is 2, that means your hybridization must be sp. 1s and 1p together, 1 plus 1 gives you 2. And the shape of that would be linear. And so the hybrid orbitals for that CH bond will be the sp hybridization on carbon and the s orbital on H. So this is similar to what we have done in chapter 1, quiz questions. I remember 1 or 2 questions from your quiz, so it's pretty pertinent. All right, next question. Which molecule is RZ7-methoxy 2,7-dimethyl 4 da 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 da? Well, if you notice, all of these are exactly the same molecule, but they vary each other in two things. A, the stereochemistry of this part, and B, whether something is E or Z. Now notice there are two double bonds, but you cannot say anything about this part right over here because it has two hydrogens, so the E and Z does not matter. So that E and Z is actually, that holds true for the other double bond right over here. So now if you look through your structure, your double bond, and you pay attention to the high priority and low priority, you can say that the hydrogen is over here, which means the high priority group is on this side. And when you compare the priority group for the other part, you would say that in this case, the high priority group is right over here because it has a double bond, so that means you're going to count that as 1 carbon, 2 carbon, 3 carbon, which are also connected to carbons. On the other hand, you have here hydrogen atoms. So the two high priority groups are on opposite sides, which tells you that this is going to be an E geometry. So basically you're seeking a structure in which the double bond is on the same side, and so this is an option, and this is also an option. The other two, A and D, you can simply get rid of those. Notice that B and C differ from each other now only in terms of the location of whether the OCH3 is pointing towards you or whether it's pointing away from you. So let's give the priority order for those. Oxygen gets the highest priority, of course. After that, you will have the double bond. After that, you'll have the ethyl, and then you have the methyl. So keeping the methyl away from you, you want to go 1 to 2 to 3. Sounds like you're going clockwise, and that means that this will be an R geometry, and that means that the other one will be the S geometry. So since we are seeking an R and Z, this is the combination that we have. So C should be your pertinent choice. Okay, next question is choose the incorrect statement about reactions of haloalkanes proceeding by SN2 mechanism. This is a pretty direct question, actually, if you think about it. There are several statements that are given about SN2. The first one is order of reactivity is methyl followed by primary, secondary, and tertiary, and that we know is a true statement. Rearrangements are common. That does not sound very nice. The reason for that is because rearrangements require the formation of a carbocation. And recall, SN2 is a reaction in which the attack on your electrophile and the loss of the leaving group, both of those takes place at the same time. So you never actually have a situation where you actually see a C positive charge. It always just remains a delta plus, and since you don't see a full positive charge, the leaving group leaves and the nucleophile attacks at the same time. Hence, that doesn't sound like a very accurate statement. So that might be one of your contenders, but let's still go through the rest of those for the sake of argument. Inversion of configuration, of course, that's one of the parameters, one of the characteristics that you see for SN2. Reaction rate depends on concentration of nucleophile and haloalkane. That is true as well. SN2 itself means it's a bimolecular reaction, so rate is equal to K times nucleophile times the haloalkane, and then the reaction rate is generally faster in polar aprotic solvent because they do not generally solvate your carbocation. So everything is true but B, and that is the appropriate answer. Okay, the question is, in addition to the expected ether as a product in the following reaction, a second isomeric product is formed. Choose the correct structure for the second product. And they're just saying, use your knowledge of mechanistic organic chemistry to predict the correct product. So we really don't care whether you've seen this reaction previously or not, but how would you move the electrons? That's what you have learned in Organic 1, and that's what this question is asking about. So let's talk about the question. Notice we have a haloalkane over here, so that will have a slight delta positive. Br will be negative. How will the reactions move, or reaction arrows move? The negative charge, notice that is at an alternate position with respect to the double bond, so you can actually have the reaction occur at this particular carbon atom, and there is resonance. Yes, you got that. And when that happens, bromine is going to leave. So your product is going to look like a double bond O on top and then a methyl at this position. Let's see if there's a choice right over here. You cannot connect, notice you cannot connect the O and the Br together because that will be two negatively charged species coming together, and that's not a accurate choice. Likewise, if you consider Br negative, and we just showed you that carbon is in the format of a carbanion, so that's a bad choice too. You cannot show, you can't just put methyl groups anywhere and everywhere. So take your time with it. Don't forget resonance, absolutely. And the product that I circled, that will be the appropriate choice. All right, let's go forward. Next question is, choose the order that has the following hydrogen atoms correctly arranged with respect to increasing acidity. So you have three different protons, and they're asking which one is least to most acidic. So hopefully you can see that the first one that I have right over here, H3, that is connected to a carbon. The second one that's connected to a carbon, which is connected to a carbonyl. Carbonyl means oxygen is electronegative, and then the HI is connected to two electron withdrawing groups. So that should tell you, we learned that through the cardio in class, that closer or more number is of the electron withdrawing groups, greater is the acidity. So the HI or H1 is going to be most acidic, H3 is going to be least, and so D should be your appropriate choice. All right, looks like something about IR. So I have an IR, and I'm supposed to figure out which structure actually gives you the appropriate IR. So let's take a look. Couple things here. Notice you have a peak going down around 2500, and it goes up to about, it's pretty broad, it goes up to about 2900-ish or so. There is one peak that you see, which is a strong peak, looks like around 3300. There is also a peak at 2200, so that should tell you, 2200 should tell you that it should be a C triple bond N or a C triple bond C. We don't have a nitrogen in any of the choices, but we do have a C triple bond C in 3 of them, so A and B automatically are out of the window. I do have a 1700, so that should tell you that there should be a carbonyl. Guess what? All 3 of them have a carbonyl. But the broad peak that you're seeing, that is pertaining a carboxylic acid, C double bond OOH. So the OH, as you know, that comes in pretty broad. So now my choice is restricted to C and D. One is an internal alkene, the other is a terminal alkene. Notice I have a 3300, which is corresponding to the CH of an alkyne, so your most appropriate choice is D over here. Next question is, choose the order that has the following compounds correctly arranged with respect to increasing melting point. Notice all of them are carboxylic acids, and hopefully they have the same number of carbon atoms as well. Let's just count that for the sake of argument. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Looks like they do have the same number of carbon atoms. The only difference that they have is that one contains more number of double bonds. That's one thing. And if you consider the nature of the double bond, all of 2 of these are cis. One is a trans. In this case, you have a trans. And in this case, you have the cis. And you know that cis alkenes are going to be more unstable as compared to trans, so they are higher in energy. And that would mean that the melting point, the lattice that you would see in case of a trans molecule, is going to be much more stabilized. So this is going to have a higher melting point than the cis one for sure. And if you compare 1 to 2 and 3, it's going to differ from them in terms of the number of hydrogen atoms. So the molar mass is going to be like 4 units smaller. And so you expect it to be the least. So between the 3, you should say 1 should be least, and 2 should be most, so this should be your appropriate answer. Okay, let's go forward. The question is, choose the order that has following resonance structures correctly arranged with respect to increasing stability. Notice we have 3 different structures. You have a negative charge on oxygen, positive on carbon, and there is another structure in which we have carbon to be neutral, nitrogen is holding the positive charge, oxygen with a negative, and then of course we have oxygen with a positive charge and carbon with the negative charge, which hopefully you can see should be the worst of all, because the more electronegative element is going with a positive charge, and that is not allowed. So if you were to compare the 3 structures, 3 with the minimum stability is the most appropriate one, and so your best structure here is going to be that. Okay, the next question has, you have to choose the order that the following compounds correctly arranged with respect to the increasing boiling point. Notice there are 3 compounds and they have just been arranged in different orders. You have one which has only hydrogen bonding. You have another one which has only van der Waals forces of interaction, and the third one has dipole-dipole interaction. So this is basically a test of essentially which force of interaction is strongest. And so hopefully you can see that the van der Waals forces of interaction, the van der Waals, those are going to be least stable followed by the dipole-dipole, followed by the hydrogen bonding. Those are very stable, very strong, and so the melting point and boiling point also is going to be significantly higher as compared to the others, so E is the appropriate choice. All right, let's go forward. Next question is, choose the correct statements about the following diagram. The diagram is given, looks like it's an exothermic reaction. Looks like between the two products, the energy of the first product, P1, is higher than the energy of P2, so 2 is a valid statement. The formation, because this activation energy is smaller, so it's going to be faster. So first is correct as well. And then both P1 and P2 are lower in energy as compared to R, so 3 is valid as well. So is there a choice? Yep, A is your appropriate choice. All right, the question over here is, which one of the sequences below is the best synthesis of E3-hexane? And I already struck off 2 because they are not pertinent to organic 1. So B, C, D, we're going to select it in between. So you're given an acetylide type species, which is subjected to reaction with a primary halide that will go through a substitution. And so you're going to end up with carbon and then 3 carbon chain attached to that. Next, we connect it to sodium hydride. So again, you're going to generate the anion, and then we are going to subject that to, again, treatment with methyl bromide. So attack occurs, bromine leaves, and now we are using sodium and liquid ammonia. So that does give us trans, and so your reaction product from the alkyne sequence was this. So you have 1, 2, 3, 4, 5, 6 carbons, but you're supposed to have a 3-hexene, and looks like this is going to give you a 2-hexene. So let's see if other sequences would work. The H2 Lindlar's catalyst cannot work because that will give you a cis-alkene. So cis and zane kind of, in this case, will go hand in hand because it's a di-substituted situation. And that leaves us with D. And just to make sure, let's see what we will get. The first sequence will give me the formation, the addition of an ethyl. The second sequence will give me the addition of the other ethyl. And then when we treat it with sodium and liquid ammonia, it's a trans addition that will give you the E3-hexene. So that will be your final product. We have a question. We have 2 double bonds, and that is being subjected to hydroboration reaction condition, and we are supposed to provide the product. Realize hydroboration reaction condition follows anti-Markovnikov's rule. That means the carbon which is less substituted should be the one that gets the OH. That means it will be this carbon and it will be the terminal carbon. Those are the 2 positions that should end up with your product. Seems like this is going to be your appropriate product. All right, next question is also based off of that. We have a methyl cyclohexene, which is being subjected to hydroboration, and then we have a tosylation, and I'll talk about that in a second. It's nothing fancy, but let's see how the reaction goes. Well, first thing first, the tosyl, that part basically converts the OH into OTS. And that just makes it a good leaving group. So you can consider this similar to, maybe HCl, treatment with HCl, for instance. And then we are subjecting that to I-, which essentially is a good nucleophile. And so we'll subject the reaction mix to an SN2 type of a reaction. So your first step is going to basically provide your OH in the least substituted sense. So your OH is supposed to go over here. Now the question is that you need to remember is that hydroboration is a syn addition, and that means that if your methyl is going to point, let's say, on top, then your OH should come from the bottom. That's one possibility. The other possibility is that if your methyl is down, then your OH is going to be on top, and so would be your hydrogen. So that's what syn addition means. The second step basically converts the OH into OTS, so that's nothing fancy, and you can, consider that as OH2 with a positive sign, nothing very different about it. And now we are treating it with a good nucleophile, so I minus, and so realize that the I minus is going to attack from the side opposite of the TS. That means if it's pointing up, the I minus is going to attack from the bottom. So at any given point of time, the I and the CH3 should be in the same direction, and looks like C would be the appropriate choice for that. Now the next one, you're not going to probably see, something to draw because you have to go click, click, click for the final, but it's an interesting question. You're given an alcohol, which is a chiral alcohol, and you're supposed to treat it with HBr. And notice what you're getting. What you're getting is a pretty similar looking molecule. The only difference is that the OH has now been replaced by Br. And the question is asking you that your reaction mechanism must be consistent with the observed stereochemistry. Notice that if this were to go through, since it's a protic situation, your SN1 would say that there should be racemization in the reaction mix. And if you consider SN2, because this is a secondary system, then there should be inversion. So is this a typo? No, not really. How do we go about it? Well, the first step would be that you are going to generate the protonation. And so H is right over here. You have OH2, Br, H, and H. So Br is essentially pointing on top. And the OH2, being a good leaving group, now is going to leave. And as it leaves, it's going to leave behind a carbocation. So I'm going to show that on this structure. That's your positive charge. Notice that the Br is right on top and it's close enough. So what can happen is that bromine can simply, for the reason similar to what we discussed in case of polarization and polarizability, when we first did bromination, this Br can now just start sitting. It can give its lone pair of electrons and just form like a three-membered ring, like the bromonium man. Exactly. And that would block one of the faces of the bromine, and so your incoming Br negative has to come from the bottom, and that would give you the chiral product. That's it. Simple enough. All right, let's go forward. The question is, you have to predict the major product, and again, I'm not going to ask you to draw the product, but I can always ask you to pick the product, and so you should know how to go about it. The first question is, and again in this one we will not talk about this one. The first question is, you have an alkene. We are treating it with an alcohol and acid. So first things first, get the nucleophile going. It will pick up that proton and it will give you the most stable carbocation, like a tertiary carbocation, and your nucleophile is going to attack, and this can attack from top or bottom because it's a tertiary center. So you end up with an OCH3. Just for the sake of argument, I'm going to say it's going to be racemic. And oxygen currently has a positive charge. And of course, whatever your solvent is, whatever is the conjugate base is for that proton, let's say it was done in presence of Cl, then that Cl negative is going to pick up that proton and relieve the positive charge on oxygen. So your product looks like an OCH3 with racemization. The other question is that you have this big bulky group and you're subjecting that to ozonolysis and followed by zinc and acetic acid. So that's pretty straightforward. All you got to do is you have to cleave at the double bond and you have to generate two carbonyls. So your product should look like as fancy as it does. That's actually pretty straightforward. The ketoaldehyde is what is going to get obtained. So just be careful whenever it's ozonolysis. Double bond is the one that goes through the bond cleavage and gives you ketones or aldehydes, as the case may be, from your structure. Okay, the next question expects you to choose the answer that gives the correct number of sp3 bonds in the following structure. That's pretty straightforward. Anything that has a double bond is going to be an sp2. So this is sp2, 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 sp2. And you're supposed to go for an sp3, sp3. So even the one in between is not going to be counted other than what you have. There's a methyl there, so don't forget that one. This is sp3. This guy is sp3, and so is that. So that's an sp3 overlap. This is an sp3 overlap, and so is that. So there's total 3 sp3 bonds. Other than that, all of them do show an sp2 hybridization. In this particular case, you have a tertiary alkyl halide which can go through an E2 elimination, and we're comparing that to secondary, which can also go through an E2 elimination, or E1 as the case may be. It depends on the reaction conditions. Recall from the video that the E2 elimination requires the entire periplanar geometry, and that's basically the only requirement. So you can't, unlike the SN1, SN2, you can't quite just say that you need a tertiary system will automatically go E1. You can't say that in case of elimination reactions. There are some elimination reactions which will go through an E2. But the one thing that I would definitely say is, because it's an elimination, because it's an anti-periplanar geometry, it's the kind of base that you're taking, one, and whether that proton that needs to be removed. So for instance, if this is the proton that needs to be removed, how accessible is that? If that proton is not very accessible, you are going to have a hard time, and the reaction is going to be super slow. So realize that secondary with E2 is not a good option, because that hydrogen is kind of hiding between the two methyls. So sterically, it's a hindered situation. On the other hand, if you consider the first reaction and the beta hydrogens in that case, those are pretty accessible. So those can be removed significantly well. E1 reaction mechanism is always going to be a little bit slower as compared to E2. The reason for that is because it requires the formation of the carbocation. So recall that the rate determining step for the formation of the carbocation, unless that carbocation gets generated, the proton will not be lost. So that is the rate determining step, and for that reason, you would say that E1 will always be slower. And since we are looking for the fastest reaction, in this particular case, reaction 1 with E2 mechanism will be the most favored one. The question asks you, two major products with the formula are formed in the following reaction, and you have to choose the structures of these major products. So what are the options? Now realize, what do we have? We have an OH in the system. We have a good leaving group. Now that good leaving group, ethanol, is a protic solvent, of course. In this particular case, ethanol is not like the greatest nucleophile, first off. And the other thing is that in terms of a base, it's not really a fantastic base, but realize that that Cl negative can generate a base from there. The important thing to realize here is that you are doing this reaction at 40 degrees, so elimination should be a product one way or another. And since in this case your your base that you will generate. So when the Cl leaves, let's take it step by step. So when Cl leaves, it's going to leave behind a carbocation, and like I said, intramolecular reaction, snake biting its own tail, is always going to be more facilitated than intermolecular. So one of the species that you are going to get out of this is 3 for sure in terms of substitution, intramolecular SN1 type of a reaction. The other thing that can happen is that Cl negative can either generate the ethoxide from ethanol, or Cl could actually pick the proton itself. Either way, the beta hydrogen is going to be lost from here because it itself is not a bulky base, and so the elimination product that you will get will be 1. So there should be a choice like 1 and 3 right over here. The next one, I'm not going to reason out, I'm just going to give you the answer that it should be this one, but I want you to reason out why that would be based on what you know from the first chapter. Alright, the next question is choose the number of hydrogen nuclei and the number of lines you would anticipate at position 1 and 2. 1 is around 5, so that should be for the hydrogen over here right next to your ketone, and 2 should be the one which should be a little bit more in the upfield zone. I would have expected this one to be a little bit more upfield for both of them, but anyway, we'll go with what they've given. So I'm seeking that 1 is the one with 1 proton only, so A, B, and C are my appropriate choices. D and E are out of the window already because we are looking for only 1 proton at that particular position. And since it has essentially 6 neighbors, that means it should show up as 7 peaks. Likewise, the 6 hydrogens for the terminal methyls should show up as 2 peaks, like a doublet. So choice C is appropriate. Next question is choose a major product. So again, it's a reaction sequence we're talking about. So you're given an alkyl halide which is being treated with OET with a negative sign, and then we are doing some kind of a bromination. So first things first, that should give you a hint itself that OET must act as a base, because this reaction condition, the Br2 with water, that is something you have seen for the formation of bromohydrin, and the reaction takes place on a double bond. So you have to generate a double bond. Essentially, you have to generate a double bond that looks like an alkene, that looks like this. That's what you have to generate. Okay. And so that's the product of the first step. And when you subject it to bromohydrin, you first will get your 3-membered ring, and the ring will open in a manner such that the carbocation is the more substituted one, which is where water is going to attack. So it looks like choice C should be the most appropriate case. Hopefully you recall that the epoxide is going to be generated from MCPBA. The dihydroxylation is for the osmium tetroxide. The OET would just be a substitution reaction, and this is just anti-Markovnikov manner, so those are not appropriate choices. How many products will be formed in the following reaction? So again, all you have to look for, how many products? Only 1 product. Will be formed in the reaction. You're carrying out ozonolysis, and basically realize that you have to cleave at each of the double bonds. So you're going to end up with a tetracarbonyl containing product. But the number of products that you're going to see is going to be 1, because even though it's a double cycle, it will look like your product. And your ring, there is a double bond O, This is an aldehyde, so that's a terminal aldehyde, and that's a aldehyde as well. So notice that everything is connected, all the ketones and aldehydes, they are connected to the same linkage. It's a direct connection, so it will be one product. If you had a double bond, let's say at another location, like maybe over here, for instance, then, or maybe over here, then it would have cleaved into two fragments, and that would be a different scenario altogether. All right, next question is, the thioacetate ion reacts with methyl iodide to give a product. Give the structure of this product. Again, this is, I'm not going to ask you to draw anything, but you have to pick, so this could be worded differently. But realize what can happen over here. Always be aware of resonance. Sulfur gets a negative charge, so you have one resonance structure where sulfur has a negative charge. You have a double bond O, you have a methyl. That sulfur is going to attack the primary center. Iodine is going to leave, so now your product will look like C double bond O S with a methyl. And that will be your final answer. All right. The next question requires you to propose a structure. And again, various different structures could be given to you. It says that you have a C6H8O2, so DOU, getting that going is the first thing I've taught you. So 6 minus 8 over 2 plus 1. There are no nitrogens, etc., so you don't have to worry about that. So it looks like you will have about 3 degrees of unsaturation. Notice over here you have like a 2200. Since you don't have a nitrogen, that better be a triple bond. You have a pretty broad peak in this center, and you also have a 1700, so that's reflective of a COOH, and I know that that's true because there is a peak almost close to 10, which is a COOH. So that's a terminal site. This triple bond will have to be internal triple bond because you don't see, the 3300. You don't see that. So we don't have to worry about that then. But looks like we have taken care of the entire amount of degree of unsaturation. And now it's a question of putting the remaining 3 groups. So notice we have a triplet. That means it must be connected to 2 neighbors. We have another triplet, which means this is connected to 2 neighbors. And then we have a multiplet, so not much can be said about that. Now notice the possibilities for this compound would be the ones that I have drawn. Since we have a triplet worth 3 hydrogens, and we have another triplet worth 2 hydrogens, that basically tells you that this guy and this guy, both of them have 2 neighbors, and they can be split, multiple times, and which is why we call it a multiplet. You would not see that in the other 2 structures because this guy doesn't have any neighbors, so that should show up as should have shown up as a singlet. This methyl would still show up as a triplet, and you should have seen a quartet, and we don't see that. Likewise over here, the 3 methyls should have shown as a singlet, and the 2 CH2s as 2 triplets. So the multiplet and a singlet, they don't match up, and so your correct structure is right over here.